Robert's a world-renowned expert in the physics of the early universe, quantum cosmology, string gas cosmology, and he's been a mentor to literally, thousands of people around the world, all of whom have gone on to, try to approximate a sliver of Robert's greatness. So it's a great pleasure to have Robert here in person, and I can't wait to hear this wonderful lecture. Thank you, Robert.
So you see, I invented my own title for the seminar series, Particle Cosmology Seminar, because I think I have something to tell particle physicists and something to tell astro and cosmology people. So this is why I call this a Particle Cosmology Seminar. So I'm going to talk about searching for cosmic strings in new observation windows. And as the title knows, I've been working on cosmic strings for quite a long time, on and off. And what is new compared to the old work that we did on cosmic strings is really the new observational windows. So this is the outline of the talk. I'm first going to remind you what cosmic strings are, why they arise in certain models, and why they persist to the present time. That's the important thing, they persist to the present time. Now, cosmic strings come in two types. And since I have this big whiteboard, I'll make a sketch, which I'll come back to later. So at late times, if you are dealing with a particle physics model that has cosmic string solutions, then if you draw a Hubble patch, Hubble horizon patch, then the distribution of strings in this Hubble patch will involve a few long strings and a distribution of loops. And the loops come about, as I will explain later, from the dynamics of the long strings. So in the second part of the talk, I'm going to discuss observational signatures of the long strings. And the long strings give beautiful signatures in position space, which we have to look for using position space statistics and not just 2-point functions or 3-point functions. And then in the third part of the talk, I will then turn to the effects of cosmic string loops. Specifically, I'll talk about how cosmic string loops can explain the abundance of supermassive black holes, which have now been observed at high redshift, and why they dominate the mass function of nonlinear stuff at high redshift. So this is the menu for this after lunch talk. So let me begin with the definition of cosmic strings. So a cosmic string is a linear topological defect in a quantum field theory. And for those of you who have not taken quantum field theory, it's interesting to think in terms of analogies. So a very rough analogy is line defects in crystals. So again, some metals, if you cool them, they form crystals with line defects, other form crystals with planar defects, yet other form crystals with point-like defects, and some have no defects. And it's a similar situation in particle physics models beyond the standard model. Some give you planar defects. Those models are already rolled out by cosmology. Some give you linear defects. Those are the ones that I'll be interested in, and so on. Now, a better analogy is vortex lines in superfluids or superconductors. And the difference, so the formation process is very analogous. The only difference is that in the field theory, these defects will be evolving by relativistic equations, whereas in condensed matter physics, they are friction dominated. What's important for cosmology is that cosmic strings are lines of trapped energy density, and that this energy density gravitates, and the gravitational effects give you signals in cosmology. Now, okay, what is the relevance to particle physics? So first of all, string solutions exist in many particle physics models beyond the standard model. They are specifically predicted to form after inflation in many inflationary models. And I like to make some provocative comments in my talk. And so if I were giving the other seminar title, which I offered, namely Emergent Spacetime from Matrix Models, then I would actually say that inflationary models based on the usual effective field theory are just sick and can be discarded. They are non-unitary and violate the second law of thermodynamics. But this is a provocative comment, and it's completely unimportant for this talk. Now, some strings of there, independent of what the early history of the universe is. So, now, if you like a particle physics model which has cosmic string solutions, then cosmic strings inevitably form in the early universe and inevitably persist to the present time. This is a causality argument to Kibble. So, seeing a cosmic string in the sky would provide a guide to particle physics models beyond the standard model. It would basically tell you if you have 4 categories of particle physics models beyond the standard model, depending on what kind of defects they have, then you would have identified one of these categories. Cosmic strings are characterized by one parameter, namely their tension, mass per unit length. And this is related to the symmetry rating scale. Now, the gravitational effects are bigger the larger mu is, and the larger the symmetry rating scale. And so, therefore, looking for cosmic strings in the sky is a tool to probe particle physics beyond the standard model at energy scales complementary to those that you are probing when you do accelerator physics. So you are probing particle physics beyond the standard model from top down as opposed to from bottom up. Cosmic strings are already constrained for cosmology. There is a robust upper bound on the string tension, which is about 10 to the minus 7. And this comes from not seeing one of the predictions in the angular power spectrum of microwave anisotropies. But it's a bound that comes from the long strings. So this already has consequences for particle physics, for grand unified particle physics models that have cosmic string solutions. And even lowering the upper bound by 1 order of magnitude would have important consequences for grand unified scale models. So the message here is that even gradually lowering this upper bound is useful. We don't have to lower the upper bound down to LHC scales. Okay, so now the relevance for cosmology is that strings may do good things for cosmology. They could give you a mechanism of baryogenesis. I'm not going to talk about that. They could provide a mechanism for origin of primordial magnetic fields. I'm also not going to talk about this. I'm going to focus on the effects of loops for supermassive black holes and for the abundance of high redshift galaxies recently detected by the James Webb Telescope. So, from the point of view of cosmology and astrophysics, it is important to look for evidence for cosmic strings, because if you find a cosmic string, you may have solutions for other problems in astrophysics. So, the bottom line is that this field of looking for cosmic strings in new observational windows, I think it is very well motivated, both from particle physics and cosmology. And now for graduate students here, there is another important point. If you ask a good question about cosmic strings, if you find a new window and you ask what is the signature of cosmic strings in this new window, if it's a good question that you're asking, then if you answer that question, then you will have an important result independent of whether you see a string or not. If you see a string, then you will have discovered something completely new. If you don't see a string, you will have improved the bounds of particle physics. So for graduate students, it's a win-win situation. And I'm actually surprised that there are so few people these days working on this topic. But I'm very happy because I don't need to work under time pressure. And as Nigel knows, I'm very slow. So for those of you who had a too big lunch and who want to doze off a bit, here are the important lessons from the talk. So cosmic strings form nonlinearities already at high redshifts. In fact, the signatures of cosmic strings are more pronounced at higher redshift than at lower redshift. So if you want to find a cosmic string, you take the observational window which has the best data at highest redshift. That's a message. And I actually think that the 21 centimeter window is a very promising window. Now, more specifically, a long string forms a wake, and the wake gives rise to a non-Gaussian distribution of density with a specific geometrical pattern in position space. And it's very interesting to look for these specific patterns. And then string loops can explain the abundance of high redshift galaxies and supermassive black holes. Let me come back to the review. So we have a theory which undergoes a phase transition. It is described by an order parameter phi. It doesn't need to be a scalar field. And strings form if the vacuum manifold of the theory, so the set of order parameters which minimize the potential energy, if that has the topology of the circle. So at high temperatures, this order parameter will want to be 0. At low temperatures, the thermal confining effects go away. The order parameter will want to take on the modulus eta, but by causality, the phase of the order parameter has to be uncorrelated on super Hubble scales. That's true at the time of the phase transition and at all times afterwards. And so therefore you are guaranteed that if your favorite particle physics model has cosmic string solutions, cosmic strings will arise in a phase transition and persist to the present time. And so this is the drawing which I already have on the board here. So at late times, then this is the distribution of cosmic strings that you have to think about. At all times, this is the Hubble radius, the Hubble horizon, and the statistical properties of the cosmic strings is time independent if you scale all lengths to the Hubble length. Now, cosmic strings do come in various types. There are cosmic strings that form in gauge theories. These are local strings. There are cosmic strings which form in theories with global symmetries. These are global strings. Local strings have no long-range forces between them. Global strings do. Some strings are superconducting. And then there are also cosmic superstrings. And then, well, it's also nice to throw out research problems. And here I will throw out a research problem. There are strings which I call embedded strings. And these are defect solutions that exist in theories where the vacuum manifold is not S1. So let's take the standard electric theory. It has a complex doublet. So there are 4 real scalar fields. The vacuum manifold is S3. There are no topological defects. One of the scalar fields is electrically charged. The other one is neutral. In a finite temperature plasma, the charge field gets a plasma mass. Therefore, the effective vacuum manifold is S1. And therefore, there are solutions of the standard model theory, the electric Z string, which should be metastable until at least the time of recombination. The research problem is to work this out rigorously. And the reason why I've not been able to do that is that I don't know of the tools to do that, because we can't use zero temperature quantum field theory. We can't use finite temperature quantum field theory because only part of the system is in thermal equilibrium, part not. But maybe you have the tools now. But I'm not going to talk about this. So this is what I was saying. This is the existence criterion for embedded strings. So here we have a theory like the standard electric theory. A complex Higgs doublet, charge neutral. Only the charge field gets a thermal mass, and so therefore the vacuum manifold gets reduced to S1. Okay, so I will be talking mostly about local strings, And mostly about non-superconducting strings, only at one point I will be using currents on the strings. So let me first focus on effects of these long strings. And there are only two actors which play a role. The first actor is the so-called Kaiser-Stebbins effect. So let me again illustrate this on the board. So if you have a string which is pointing out at you, it is a straight string, then space perpendicular to the string is not R2, but it is missing this angle. It's a deficit angle whose magnitude is related to the string tension. Now, if we are an observer here, we are looking at the microwave photons coming around from different sides of the string. If the string has a velocity v, then you have a relative Doppler shift between this photon and this photon. And therefore, the signature of a long string in the sky is a line in the sky across which the temperature jumps. Now, the characteristic scale on the sky of these lines is 1 degree or larger. Sky coverage is not crucial. You don't need a full sky survey to find these signals. It's enough to look at the angular sky that corresponds to the Hubble radius at recombination. So let's consider 5 degree by 5 degree in the sky. That's a good framework to think about because it also fits into the patches which the South Pole Telescope measures and the ACT telescope measures. So in some of the slides that follow, I'll be considering 5 degree by 5 degree patches in the sky, and then you would expect to see a number of strings with an extent of about 1 degree in the sky. But to find the gradient, you need good angular resolution. So you need good angular resolution, not full sky coverage. So ACT and South Pole Telescope are competitive with Planck. And in fact, the new telescopes, like the ones that you're working on, will be more powerful because of the better angular resolution.
Robert, I should know this, but what sets the radial, the azimuth angle of the deficit angle?
Okay, that's a good question. So it is the Hubble radius at recombination. Because this is a picture at all times. If we look at the microwave background, we're interested in time of recombination and later. The most numerous strings are those around at recombination. And so therefore, even though they're the smallest ones, that's 1 degree by 1 degree. Now, the second actor is the wake. So if you have this cosmic string moving through a plasma, it's moving through a plasma. So if you're here behind the string, then you will actually see stuff moving towards you from top and bottom. And you will have a region in which you'll get twice the energy density. And once you have this region that has twice the density, it will start to pull in matter from top and below. So this is the wake. It is when a string passes by at time t sub I, it sets up this nonlinear density perturbation of extent t sub I in direction of the string, t sub I times velocity in direction the string moves, and the thickness is given by the deficit angle. And after that, this wake accretes matter, and the co-moving thickness grows linearly in the scale factor. You can show that using the Zeldovich approximation. These are the two actors, this lensing effect and the wake. So let's look at cosmic microwave temperature maps. So this is a 5 degree by 5 degree patch in the sky, and this is how the temperature distribution would be if you only had cosmic string perturbations, no other lambda CDM perturbations. So you have these beautiful, clear features. Now, if you have no cosmic strings, only lambda CDM fluctuations, then you would see this pattern. So they're very different. So let's add the two together, and let's take a string tension which is 2 orders of magnitude larger than the upper limit. Add together lambda CDM and cosmic strings. you can still see the strings. But this is 2 orders of magnitude larger. So the challenge is, let's go to a little bit below the current limit. Where are the strings now? Okay, so to answer questions like that, you need new statistics. And what we played with is we played with wavelets and curvelets as a promising way to extract this signal. This is a master thesis of Lukas Helgt, done at ETH Zurich. So you do a double wavelet decomposition. You start with this map, and at second order, in the wavelet expansion, you get this, and the string signals have appeared. So the message here is that you can find the string signals which are in this map by using clever statistics. I'm sure this is not an optimal statistic. But the message is that you can't just look in Fourier space. If you want to find the strings, you have to look in position space. So our preliminary conclusion was that using data like data from the SBT and ACT, we could get a factor of 3 better than the current of about.
Does the CMB polarization as well?
That we have not analyzed. See, okay, we've analyzed a little bit of polarization, but we haven't done a good analysis. So the CMB radiation, which is passing through a wake, that will acquire polarization. And that will acquire equal strength E mode and B mode polarization. And whereas microwave background passing through a spherical cloud will only acquire E mode polarization. So the key thing is that the wakes will produce a B mode, primordial B mode polarization signal. Now the amplitude is very small, unfortunately. We were initially very optimistic that this would be a wonderful window, but it turns out that it's not such a good window just because of the low amplitude. And also the power spectrum of the induced B mode polarization is completely degenerate with the power spectrum of the B mode polarization induced by lensing from E mode. The key scale where the spectrum turns over is not the Hubble radius at recombination, but the Hubble radius at equal matter and radiation. So there is a polarization signal, and at one point I was quite excited about it, but I'm a little bit less excited just because the magnitude is just. Okay, I'm more excited about the 21 centimeter window. So here is a sketch of a wake, and imagine the CMB, the cosmic microwave background radiation, passing through the wake. Now the wake is an overdensity of neutral hydrogen, and neutral hydrogen can be excited, the spin-flip transition, and that is an absorption effect. So via this process, string wakes give you an absorption signal in 21 centimeter maps. So if you compare microwave photons passing through a wake compared to those that don't pass through a wake, those that pass through a wake will be absorbed more, and you will have an absorbed signal with a definite signature. And here's a sketch of that. So this is space-time sketch, and this is the resulting image that you would have in a 3-dimensional 21 centimeter map. So angle in the sky, frequency, here it's space and time. So we imagine a wake which is created at this time, and well, the string will have disappeared, but the wake will persist. The microwave photons will pass through the wake, and they will give rise to this region in the 21 centimeter map with extra absorption. So again, the typical angular scale of this feature is 1 degree by 1 degree in the sky. Now, the thickness of the wake is very thin, and that's reflected in the fact that the frequency width of the signal is very small. So let's be quantitative about this. This is the formula for the brightness temperature in 21 centimeters. So this is the absorption, and this would be the emission, but this is the more important one. And what we want is we want to calculate the difference in the brightness temperature compared to the brightness temperature of photons which don't pass through wings. So this is the quantity which is measured in 21 centimeter surveys. So the two quantities that you would like to know is what is the thickness in frequency space of this absorbed signal and what is the magnitude in temperature. And it turns out that the magnitude in temperature is 200 millikelvin independent of the string tension. And compared to 21 centimeter signals of lambda CDM, this is an enormous signal. And this is a very small number. And this is G mu in units of 10 to the minus 6. So if you want to find this signal in 21 centimeter maps, you need good frequency resolution. Okay, this is a map where the string signal is superimposed on the lambda CDM signal. It's a 5 degree by 5 degree patch of the sky, so the string is 1 degree by 1 degree. And compared to lambda CDM signatures, it is an enormous signal. Now, it is hard to identify because we are talking about high redshifts before nonlinear stuff becomes important. So we're talking about redshifts greater than 10. And the noise in 21 centimeter surveys grows dramatically at high redshift. So we have to fight the noise. Also, the experiments that measure 21 centimeter are typically interferometers, and they collect data in Fourier space. So such a wake signal will produce this kind of Fourier space feature compared to a spherical blob, which will produce this type of signal. So if you deal with Fourier space data, then the challenge is to pick this signal out from this one. Okay, so we did a rough analysis to see whether the 21 centimeter can actually be used, including the effects of noises. There are all kinds of noise sources: galactic synchrotron, point source, galactic free-free, exogalactic free-free. So we modeled them. We model all of them as Gaussian processes, but with the right amplitudes and frequency dependencies, which we read up in the literature about these. So we included the noise, but the caveat is that all the noise sources we model as Gaussian processes. That should all be done better. Now we were asking, can an existing experiment like MWA, Murchison Wide Field Array, prototype of SKA, an instrument which is already taking data, can this detect the signal given the noise? So these are the parameters of the noises that we included. Again, we included them all as Gaussian processes. And we even included MWA noise. Then we chose a statistic which is sensitive to the Fourier space ridges in the string signal. And it's a statistic, but it is not at all optimal. It only uses two-dimensional information of the three-dimensional survey. There's a huge potential here in improving the analysis, and we are working on that. So, given some other technical things, we found that the signal of a cosmic string wave with a string tension a little bit lower than the current bound can be identified in a statistically significant way by looking at redshifts of about 12. And so I'm optimistic that with better statistics, using a full three-dimensional, we can go several orders of magnitude lower. So this is why I feel that the 21 centimeter window is a promising window to find signals of cosmic space. Okay? Good, so this was some aspects of looking for signals of these long strings. Now, let me turn to signals of loops. So there are two applications. One application is using cosmic string loops to seed direct collapse supermassive black holes at high redshift. And the other application is just to get a larger number of high redshift galaxies. The first evidence, first experimental data is that black holes with masses greater than 10 to the 9 solar masses have been observed at redshifts greater than 6. And if you assume that accretion of matter onto a black hole is bounded by the Eddington rate, then in order to explain the abundance of these high redshift galaxies with such a big mass, then high mass nonlinear seeds are required at early times. And in the lambda CDM model, the probability of nonlinear seeds at high mass is exponentially suppressed as a function of redshift. And this is illustrated here. So redshift of 6, we want to get black holes with these masses. So this is mass, this is redshift. This is accretion at Eddington rate. So if we want to have our seeds at redshift of 30, then you need seed masses of more than 10 to the 3 solar masses, redshift of 30. So now let's look at the number density of seeds, nonlinear seeds with mass greater than this mass as a function of redshift. Okay, so if you go back to redshift of 30 is here, then you see that, well, if you want to get one of these seeds per supermassive galaxy, the seeds that you're working with is 10 to the minus 3 solar masses. Okay, so the bottom line of this is that in the standard lambda CDM model, there are not enough nonlinear seeds at high redshift to allow for supermassive black hole formation at high redshift. Now, cosmic strings can come to the rescue because strings give rise to nonlinear density perturbations at arbitrarily high redshifts. You don't need as you have more seeds available at high mass at high redshift. And this is a corresponding slide to the one that I showed previously for the lambda CDM model. It shows the mass of the nonlinear seeds that you have at a particular redshift if you want to get a number density of 1 per supermassive galaxy. So these curves are only power law suppressed as a function of redshift, as opposed to the curves in the lambda CDM model, which are exponentials. So if you have a model with cosmic strings and lambda CDM model, and cosmic strings with these various values of the string tension, very low string tension, you basically find that at high redshift, the mass function of nonlinear seeds is dominated by the cosmic strings. Okay. So, now, if you want to form a black hole from the collapse of matter onto a nonlinear seed, you have to make sure that the matter that collapses onto a nonlinear seed does not fragment. It has to uniformly contract beyond its Schwarzschild radius. So this is the additional challenge that you're facing. Now, in the standard model of getting supermassive black holes forming astrophysically, you typically assume that you have one galaxy where there's been star formation, another very close by galaxy where there's no star formation, and the radiation from the galaxy that has star formation prevents the gas in the galaxy that had no stars from fragmenting. So that's a usual mechanism. Here, what we are going to use is radiation from the superconducting cosmic string to give us the radiation in the object that is the seed. Okay.
Question, Robert. So it isn't necessary that you get it to collapse directly into a trapped surface. I mean, you could make a supermassive star.
Yes.
And that will wind up as a hole.
Yes.
If it's above a mass of like 10,000 solar masses or something like that.
Right. But then you're again faced with the problem of not having enough seeds to form this high mass star.
Well,
Anyway, we are going the other way.
I'm just saying that your mechanism
Yep.
of getting the fluctuations, the initial seeds there.
You mean that could also work through getting a supermassive
Correct. I'm just saying you don't need to actually have
Correct.
it collapse through
That's a good point.
the trap surface. You can
That's a good
actually
point.
have it just make a self-gravitating configuration that will be GR unstable.
Yeah, that's a good point, and that might work for non-superconducting cosmic strings. Okay, so here's what I said: you have to prevent the collapsing cloud from fragmenting. And the way that we do that is we have enough Lyman-Werner radiation, so electromagnetic radiation in the Lyman-Werner regime to prevent the fragmentation. And for that, we need the cosmic strings to be superconducting. The superconducting cosmic string loop will radiate both gravitationally and electromagnetically. So this is a challenge. We need to demonstrate that the mass collapses inside the Schwarzschild radius. Well, that's what we want to demonstrate. So here are the conditions that you have to satisfy. If you want to get this direct collapsed black hole, you have to have sufficient mass greater than the Jeans mass. You have to have sufficient virial temperature. And then you have to have no heavy metals, because that would trigger fragmentation. And then you have to have no molecular hydrogen formation, because that would trigger fragmentation. So with cosmic string loops, you have a distribution of loops. You have a large subset of loops that have this seed mass. Using the Zeldovich approximation, you can compute the virial temperature of the stuff that accretes around the loop. And you find that if you have a seed of this mass, you automatically have a virial temperature greater than this. We are talking about high redshift. There's been no star formation, so therefore there are no heavy metals. So these three conditions are trivial. This is a key condition. Okay. And so this is a mass condition. If you have a loop of radius r, its mass will be mass per unit length times r times 2 pi. And then the baryon, we only talk about the baryonic mass. The baryonic mass will be suppressed by this. And this is the growth of the mass by gravitational accretion. So here I took a loop that is around at equal matter and radiation. It grows in mass between equal matter and radiation and the time that you're looking at. So this is a condition that you satisfy, and there is a range of loops with radius smaller than the time of equal matter and radiation, which satisfies that condition. So the only condition that we really have to work on is we have to get enough electromagnetic radiation. So to do that, we assume that the strings are superconducting. They have a current, second parameter, not only mass per unit length, but current. And if you have a string with a current I, then this will emit electromagnetic radiation according to this frequency distribution. So what we can do is we can simply integrate up all the photons that are at the time that we are interested in black hole formation in this energy region. And not surprisingly, you find that there is a range of currents for which you get enough Lyman-Werner radiation. And this is the result. So here we have our two-parameter family of superconducting cosmic strings. We have the mass per unit length, we have the current, and there's this window here where you can satisfy the direct collapse black hole criteria. So these are the lessons. We get the right number density of such black holes as well. So now let me turn to the last topic, and this last topic is the abundance of high redshift galaxies. So the James Webb Telescope has discovered an unexpectedly large number of high mass, high redshift galaxies. Caveat that most of these redshifts have only been determined photometrically, not spectroscopically. So we have to be a little bit careful, not over-interpret the results. But if you take the results as they are presented now, then in the standard lambda CDM model, you have insufficient number of high mass, high redshift seeds to explain these galaxies. And so, question is, can cosmic strings provide an explanation for the data? So, here you see the mass, here you see the energy density, and these are the preliminary JWST data, redshift 8 and redshift 9. And here you see a prediction of lambda CDM for these two different redshifts, very different, and both below. So if this data is really robust, then there's a problem. Now the point I'm not going to make is that with cosmic strings we solve this problem. But the point I'm going to make is that independent of what the data actually is, cosmic strings dominate the mass function of nonlinear stuff at high redshift. And here's an illustration of that. So if you look at the mass function, so dn dm, d log m, so m is a mass, n is the number density, r is a function of the mass, and we compare a pure lambda CDM model with a pure cosmic string model, then we get these mass functions. So today, you see that lambda CDM totally dominates the cosmic string contribution. Go to a redshift of 20, cosmic strings totally dominate lambda CDM. And this is for a string tension of 10 to the minus 10, which is 3 orders of magnitude and the robust bound.